Thank you so much for joining us, both in person and online, for this special session of the Engage series, organized by the Goddard Office of Communications, the Earth Sciences Division, and the Goddard Scientific Colloquium. Good afternoon. I'm Dahlia Kirschbaum. I'm the Director of Earth Sciences Division here at NASA's Goddard Space Flight Center. We are truly honored to have environmentalist and former Vice President Al Gore as our special guest today. After Mr. Gore's remarks, I will lead a panel discussion on remote sensing and the future of Earth observations. Each panelist will provide a brief overview of their work and followed by a live Q&A session. But before we proceed, I would like to invite NASA's Deputy Associate Administrator, Casey Swales, to say a few words. Casey.
All right. Good afternoon, everyone. Is this working? Can everyone? Okay, there we go. Yeah, good afternoon. It's always an honor to be here at Goddard, NASA's premier science center, and to see all of you in the audience. But today is a little extra special, of course. Vice President Gore, just thank you so much for being here, taking the time to visit, to speak with the workforce, because it really means a lot to everyone. But more importantly, thank you for being one of the most influential voices in our country on such an important topic, climate change. So thank you very much. I think it's safe to say that your words and your actions over the years have inspired much more than just the Discover mission. And so today's engagement session is particularly appropriate, titled Remote Sensing and the Future of Earth Observations. And if I can say this, it doesn't get much more Goddard than that, because this really is the group that makes that happen. This is where scientists like you all have been studying the Earth and the rest of the universe for more than 65 years. So truly an incredible and talented group of individuals. It's the birthplace of TIROS-1, the world's first successful weather satellite, of Landsat, the longest running Earth observing mission in history, and of course the legendary Earth observing system, including 20 years of Aqua, Aura, and Terra. It's also home to the world's largest collection of Earth scientists who use that remotely sensed data to publish more than 400 journal articles every single year. So it's scientists like all of these individuals in the audience, along with many more across the world. So it will be you and your successors who will also make NASA and Goddard the future of Earth observations. So thank you. You are continuing to accelerate core science research to enable action through the newly established Earth System Observatory Project Office, the Greenhouse Gas Project Office, and flagship missions such as the Atmosphere Observing System and Landsat Next. And so on behalf of Administrator Nelson, thank you again, Mr. Gore, for all that you've continued to do and for visiting, showing your support for this incredible workforce that we have here. And thanks to all of you, the Goddard scientists who make this a reality every single day and have led the way in observing our home planet in space for more than 6 decades. Thank you very much.
Thank you very much for those words of support. So now it is my distinct honor to introduce today's special guest, a visionary leader whose dedication to our planet has inspired generations. Former Vice President Al Gore is not only a powerful environmental advocate, but also a central figure in advancing critical discussion on climate change and sustainability. In addition to his many decades of political leadership and his Nobel Peace Prize for increasing public awareness of climate change, many of you may know him for his groundbreaking documentary, An Inconvenient Truth, which raised global awareness about the climate crisis. Here at NASA, we also know him for his pivotal role in inspiring one of our most iconic missions, Discover, originally known as Triana. This mission, born from his vision of providing continuous views of Earth, has delivered vital data that informs our understanding of the climate and supports decision-making processes shaping our future. From his tireless advocacy for climate action to his role in launching innovative missions like Discover, former Vice President Al Gore's commitment to environmental stewardship is both transformative and enduring. Please join me in welcoming former Vice President Al Gore. Thank you.
Thank you very much. Thank you, ladies and gentlemen. What a pleasure and honor it is. I hope you can imagine just for a moment what kind of feelings I have walking into this auditorium and seeing all of you and thinking back over the 10 years of this Discover mission, and really much longer than that, and as 26 years since the work began. And for those of you who have been a part of this, thank you so much. For all of you who have been part of NASA and NOAA and working on space science in various ways, thank you very, very much. And I want to thank Dr. Mackenzie Listrup and the entire team at Goddard for the very, very warm welcome that I've received here today. And when I first heard that you all were planning some kind of gathering similar to this for the 10th anniversary of the Discover satellite launch coming up February, this is the 10th anniversary of the science mission, that's the core of it. I wanted to be here, and I'm really just blown away by the courtesy and the warmth of your welcome. And I want to acknowledge the Discover science team, Dr. Adam Sabo, the Discover Project scientist, and where are you? Anyway, thank you very much, Adam. Dr. Alexander Marshak, the Discover Deputy Project scientist, Dr. Jay Herman, the EPIC instrument scientist, Dr. Richard Ekman, the HQ Discover EPIC NISTAR program scientist, and the staff here at Goddard who oversaw the construction of Discover and the storage and safekeeping. I remember when former Senator Barbara Mikulski, who was really one of my closest friends in the Senate, we were seatmates on the House Commerce Committee when we were both in the House. Anyway, she called me up after it was put in. So she said, "Don't worry, Al, we're going to feed it little space snacks until it's ready to launch again." And you all, for the keeper of the space snacks, thank you so much. And by the way, those who have helped with incredibly skillful work to extend its mission year after year by maintaining the instruments, and through that brief hiatus, it picked up fully, and now it's got an impressive projected life going forward. So I'm very happy to know about that. And let me also acknowledge a few of the team that supported the very first iteration of the Discover satellite and championed it over the years. And I don't think they're here, but my friend Dr. Francisco Valero, who was the principal investigator for the project in its first iteration, I want to acknowledge Francisco, and Dr. Alan Lazarus, who helped design Discover's solar particle sensor. Also, I want to acknowledge the leadership at NASA and NOAA, of course, and also the U.S. Air Force and the White House Office of Science and Technology Policy, and many leaders in the Congress. I mentioned Barbara Mikulski. I also want to quickly mention Administrator Bill Nelson, and he was chairman of the House Space Subcommittee while I was chairman of the Senate Space Subcommittee, and we also happen to be extremely close personal friends. And he and Grace, where I was with them in New York City during Climate Week just a couple of weeks ago. And of course, and there are others too, I'm not going to mention them all. Discover is just one of the many satellites that NASA and NOAA and our international partners around the world operate to better understand our planet. And of course, you'll forgive me, I hope, if I just mention a word about the unique role that Discover plays among all of the other ways we study our planet. Ever since the early days of the space program, images of the Earth from space have captivated and inspired humanity. Years ago when I was working on computer networks, a data scientist said, if you analyze the human brain in computer terms, you'd say we have a low bit rate. Bell telephone back in the day had decided 7 numbers were the most we could remember, and then they added 3. But while we have a low bit rate, we have very high resolution. And so the long struggle between the image and the word continues. And the image of our Earth from space is the single most compelling, iconic image that any of us have ever seen. We're connected to it, not only metaphorically, but literally and poetically. And when the late Bill Anders, who we lost not that long ago, captured that first image, I've listened to the audio on the NASA website, hey, quick, where's my camera? We got any color film? Give me that camera. And it just kind of really highlights how important that Earthrise image was. It changed so much, and it changed us in ways that are hard to quantify with scientific experiments. It really did open up our understanding of the fragility and beauty of our planet floating in the dark void of space. And then exactly 4 years later, that image, of course, Bill Anders took that on Christmas Eve of 1968. They didn't expect it when they came around. All of you here know the story. 4 years later, to the day, on Christmas Eve 1972, NASA released the famous blue marble image. It had been taken on the 19th of December that year on the way to the moon. And when a few days after it, no, it was taken on the 15th. No, it was taken on the 7th. That's right, December 7th, on the way to the moon. Thank you. And then it landed on December 15th when it came back. And then 4 days later, the blue marble image, after being processed from the film, was released, and it really changed quite a lot. That picture is still the single most reproduced image in the history of photography, by far. And I think the reason has to do with the sentences I strung together just a moment ago. It's iconic. We're connected to it in every dimension. And that had something to do with the proposal of the Discover satellite to be able to give humanity access to that view of where we live, who we are, what we're about, how we are placed in the rest of creation. And now we have, thanks to Discover, 50,000 blue marble photographs with an occasional photobomb by the moon. In fact, you'll see one of those photobombs. I think there have been 3 transits in front of the camera since these images have been taken, and it does kind of put things in perspective in yet another way. And when we see a complete picture of all humanity in one image, it has an impact on people that, again, is hard to define precisely and hard to study exhaustively, but it's called the overview effect, and it's supported by the anecdotal evidence of the astronauts and cosmonauts and space travelers from every nation who come back and way more often than not talk about how they themselves were transformed by seeing that image from far enough away. And so we're not only inspired by it, thanks to these incredible teams assembled here, we learn so much about cloud dynamics, the amount of heat that our planet absorbs, changes in vegetation, data on ozone, sulfur dioxide, all kinds of particulates, 2.5 ppm and beyond, and others. And to date, there are more than 100 peer-reviewed scientific publications that are based on the unique science gathered at the L1 point by Discover. And for all of the scientists who are here and those on the teams that are represented here, I want to say congratulations and thank you. And the fleet, the entire fleet of Earth-observing satellites that look back at our planet from so far away, and in the case of Discover, 1 million miles, 1.5 million kilometers away, we have been given a trove of information that is otherwise inaccessible. And they make it possible for us to make the invisible visible, and to understand what we previously saw as a mystery. And when what we now know as the Discover satellite was first proposed back in 1998, we were on the verge of a technological explosion that eventually transformed our ability to collect, store, process, and display untold mountains of information about our planet. And now that revolution has evolved into the burgeoning AI revolution, which has the potential to once again supercharge our understanding of the Earth just at the time when it becomes critical for us to understand the violent collision between our civilization as it's currently organized and the surprisingly fragile ecological systems on which human flourishing depends. And because we're here today not only to celebrate this 10th anniversary, but also to discuss the future of remote sensing and atmospheric observations, I do want to take the opportunity to encourage all of the scientists and mission specialists and engineers and space enthusiasts to think about the ways this data can be applied to address the incredible challenges of this generation of humans now alive, chief among them the climate crisis. These scientists gathered from NASA, NOAA, and throughout the federal scientific enterprise, some here, some beyond this building, you are critical to our understanding of the impacts of this crisis. It's almost impossible to convey in words how serious this crisis is. We've never dealt with anything quite like it. And of course, every day we're trapping as much heat as would be released by 750,000 Hiroshima-class atomic bombs exploding every 24 hours. That's a NASA statistic that I use on many times a day. But having the ability to understand it it's a challenge for me, even though I've spent 50 years on it. And so no wonder it's a challenge for our political systems around the world. But, you know, Mother Nature is a persuasive advocate, and I think that she's kind of got our attention here. And we saw the image, I guess that was over in the other building of Hurricane Milton, but Helena and Milton back to back. And I don't want to get down into the details of this, but we really have to do a much better job of conveying this understanding and building support for science. We were talking about that earlier. The assault on funding for science throughout the federal budget is an absolute outrage, and it has to be reversed. And by the way, this overview effect and paying attention to what human beings here on Earth can actually see and experience is intimately connected to the battle for support of science in the federal budget in all these departments. So keep that in mind when you're deciding whether or not to put a great TV camera on the replacement for the Discover satellite at the L1 point. An organization that I co-founded called Climate Trace, we were discussing this earlier, is harnessing all of this satellite data to and fusing it with other sources of data to identify for the first time where exactly the greenhouse gas global warming pollution is coming from. And late next month in Baku, Azerbaijan, I, with my colleagues, will release the new data set from Climate Trace. It's a coalition of nonprofit artificial intelligence, NGOs, data scientists, universities, et cetera. And we're very proud, by the way, to have your colleagues at NASA's Jet Propulsion Laboratory among our key collaborators. We will release the 500 million most relevant point source emission sites for global warming pollution everywhere in the world, along with the metadata, who owns it, who operates it, what technology it is, whether the emissions are going up or going down. And it was a long time ago when Lord Kelvin first uttered the phrase that has become part of the business management publishing and cottage industry. You can only manage what you measure. And we have had trouble managing global warming pollution, but now we can measure it, and we know exactly where it's coming from. And large corporates are beginning to use it to swap out suppliers and their supply chain for lower emissions. And we will move, starting with the announcement in Baku early in the first quarter of next year, with a monthly periodicity and with a linkage of the global warming pollution, thanks to your colleagues at JPL and Carnegie Mellon University. We now have machine learning algorithms that backwards engineer from the greenhouse gas pollution what the particulate pollution is. And we have the digital wind socks that vary throughout the year, and we've linked it with hospital admissions to compare how the same combustion process that creates the global warming pollution also is making people sick, killing 8.7 million people per year, mostly from combusting fossil fuels. In any case, I know that I'm running overtime. I've just got a couple of other things to say here. I want to end by quoting President John F. Kennedy's famous speech from Rice University in 1961. And I'm not going to quote the part about we're doing it not because it's easy, but because it's hard. I want to quote it. I guess I just did. But he also said, and I quote, "We set sail on this new sea because there is new knowledge to be gained and new rights to be won, and they must be won and used for the progress of all people." Well, we're continuing to sail on this sea of knowledge, and I want to just encourage you, as I thank you, encourage you to ensure that you're seizing every opportunity to reflect on this knowledge and help the public understand what we're facing. Discover is a perfect example of how to combine a scientific mission with a mechanism for public enlightenment and engagement, and its current mission has been incredibly successful and should, of course, be extended. I'm counting, and I speak for so many who are counting on all of you in this room to continue expanding our access to the knowledge we need to ensure the survival of human civilization. What a crazy proposition that we have to ensure the survival of human civilization. But that we do, and we're counting on you. And if you ever doubt that we have the political will to succeed, just always remember that political will is itself a renewable resource. Thank you very much.
Thank you very much, former Vice President Gore, for your inspiring remarks and your continued support of the earth science community. As I was preparing for this panel, I was actually listening to a podcast from 2021 with former Vice President Gore, and I hope it's okay, it's public, but he spoke about a pivotal time in his life when one of his children was in the hospital, and for an extended period. And following their recovery, fortunately, He recalled he reviewed his packed schedule, which I think many of us can relate to, and all of the meetings seemed a little less urgent, except for the climate crisis. Now, I have young children, and I really resonate with that story. We all live the impacts of climate change every day, be it air quality alerts that prevent children, like mine, from participating in outdoor activities, rapidly intensifying hurricanes that are currently causing billions of dollars of losses from Florida to North Carolina, or changing water resources for farmers in the heartland who are witnessing shifting storm patterns that affect their crop yields. As a leader in earth science for over 60 years, Goddard makes critical observations of the Earth from space, from aircraft, and the ground to provide foundational understanding of how complex our planet is and how it's changing. We integrate this information in climate models to understand our past, represent the present, and project out into the future. And it's that future piece that I would like to focus on in today's Engage session. We look to the future with profound scientific awareness that we still have a lot we need to understand and measure. But we're also motivated by the opportunity to do things differently, work with new partners, challenge ourselves to accelerate science into action to safeguard our planet for future generations. So today I am joined by three esteemed colleagues who have all provided scientific contributions, significant scientific contributions, as well as leadership beyond the agency walls. So I'd like to introduce Dr. Miguel Roman, Deputy Director of Atmospheres, Dr. Leslie Ott, Project Scientist of the U.S. Greenhouse Gas Center Project Office, and Dr. John Bolton, Chief of the Hydrological Sciences Laboratory. So I'd like to invite each of you to provide some initial thoughts and maybe a personal reflection on the topic of today's Engage session. So Miguel, take it away.
Great to be here. So I came back to Goddard 2 months ago after being in industry for about 6 years. This was always been my home, and many of you have known me since I started as an intern and crossed those gates. I'm from Puerto Rico. I'm from the Caribbean. So I've been inside the walls of a hurricane 6 times during my life. And it's interesting looking at the lived experiences of American citizens who are going to increasingly witness that experience. There are 2 things that happen when you're inside the wall of a hurricane. The barometric pressure goes down, so your ears pop. And as you're secluded inside your home and you board up all your windows, there's this sound of wind. It's a hissing sound. And in Puerto Rico, there's a folklore story of huracán. The term hurricane is a Taíno term. And huracán is the bad god. Yukiju is the good god. And so the hissing sound of hurricán now reverberates across all of Florida. And these recurring acute disasters that we're all trying to get our head around, because they're not the same as the ones for 1980, 1970. I'll start with that. That's my study of why I came back to Goddard. It's an exciting time. Now we have land hurricanes called derechos. And I look forward to telling you what we're doing to try to predict those later. Hey.
Well, I can't talk about that.
It's funny. I was born and raised by scientists. My parents met studying physics. So I would say science kind of chose me, right? But within science, I got to choose the kind of work that I do. And I chose meteorology in part because I loved that it was sort of like the most personal of the physical sciences, right? Like we all get up, weather affects our mood. It affects it's one of the first things we check in the morning. It's the first thing you talk about, with a stranger in the elevator, right? It's the thing that sort of grounds all of us. That's the background of our personal experiences. And, I loved that thing of knowing, about this air that we all swim in, right? But, increasingly, instead of being in the background, weather is now, the front pages, like Miguel mentioned, right? We see superstorms, we see fires. And these are things that are, for all of us personal. My brother lives in Nevada. He was evacuated from his home a month ago because of fire near Reno. And he was lucky. He was evacuated. His son was out of school for a week. It became the incident command center. And, nothing happened. They went back to their house and they wait for the next time, right? And there's this, in addition to those dramatic events of being in the interior of a hurricane, there's this untold cost of climate change that we all face in, lost school days, lost wages, sleepless nights of not knowing if your home's going to be there when you go back, right? And so that's really changed the kind of focus of the immediacy of climate change, has changed the focus of how, I practice meteorology, right? I do nothing that looks like weather prediction these days, but I focus a lot on greenhouse gases and how we can use basically the same kinds of infrastructure, weather models, to assimilate not just weather observations, but greenhouse gas data, air quality data, so that we can, one, ground and get a good baseline for what's happened in recent decades so that we can track, for better or worse, how the climate is changing. It's changing for the worse in a lot of ways, but there are examples of positive progress, things like recovery of the ozone hole, improvements in air quality related to the U.S. policies in the 80s and 90s. And so, with those kinds of models and satellites, we can track, the future of the planet and hopefully make some positive changes and extend those to greenhouse gases and help the community navigate what is a very challenging environment.
Thank you. I love my jobs. This is great. So I'm from West Virginia. I'm the youngest of 5 boys. From our kitchen window, we could see the Ohio River, right? So I ended up swimming, canoeing, and spending most of my time on the water. And in Wood County, West Virginia, is also known as the Chemical Valley because there's a large number of chemical plants and other industry that provide critical products for the entire world. And they also employ most of that town, including my father, who designed wastewater treatment plants. So I grew up from a very early age of having a deep appreciation for water resource management, understanding the value of protecting freshwater resources. And I can think of no better place to be because NASA is an innovator and leader in Earth systems science. And I think it's very, very important for us to continue this. Mr. Gore, thank you so much for spurring this discussion, because my journey began with a deep appreciation for the environment and a desire to contribute to the greater good, as you said. And I'm so grateful that NASA is also championing these same core values and enabling us all to contribute to better understanding our world and making a positive difference in the world.
Thank you. Thank you for sharing your stories. I think storytelling, as we know, is a really powerful way to communicate science. So let's jump into some science. So maybe start with Miguel. How do you see Goddard's advancements in technology and science helping us to predict some of the extreme weather like hurricanes or heat waves? What do we need to do going forward as well?
So the Earth observing system era that is soon to end, with Terra Aqua and Aura being decommissioned in around 2026, has given us a lot of lessons in terms of what we need to do under an accelerated set of extreme events that we're seeing, and how we need to build the future down to the hardware, right? Where we need to invest in order to understand processes that back in the 80s when we were drawing in the schematics for these missions, we didn't know we were going to have to deal with land-based hurricanes like the Urchels. We didn't know we didn't have to deal with intensification of, Hurricane Milton going in from a Category 2 to a Category 3 in 24 hours, attributed to the warming of sea surface temperatures. So we've managed to generate the entire technology toolbox to understand extreme weather events. Microwave sounders work really well over water, but they kind of fail over land. Infrared sounders can't penetrate through clouds. So we figure out back in, doing EOS, we got to combine them both, use them as a toolbox. Now we're entering into a new era where we're miniaturizing the sounders using a new system called hyperspectral photonic-based microwave systems. Each receiver that you use to get a vertical profile of temperature, water vapor, pressure, and height of the boundary layer, it's about the size of an AirPod. We can only right now, with the current program of record, get about 20 profiles. But at Goddard, just this month, by the way, we're able to slice that hurricane into 1,000 layers using photonic-based microwave hyperspectral systems. This is going to be a game changer, in part because the part that we need to be measuring is where we live. The boundary layer, the first 2 kilometers, where all the air quality is going on, where all the injection of fire from biocumulus clouds are taking place, where we have, and here's the statistics for you, 1 million stillbirth deaths per year from air quality impacts of tropospheric ozone going down. And so, exactly, yes. It's what we do at Goddard is not just unique in terms of the engineering capabilities that we only have in the center, but our conduct and focus of we're not just going to put air quality on one building and weather to another building. We don't do that. We have the entire building 33 combined working on these problems because they're an integrated problem. That is why we're rolling out this integrated Earth System Observatory. You can't separate these problems.
And so speaking about modeling and really helping us to understand that boundary layer, helping us to understand greenhouse gases, which we've heard about from former Vice President Al Gore, going to Leslie, as the lead of the Greenhouse Gas Center Project Office, where do you see NASA's unique role and how it plays in helping to advance our understanding of greenhouse gases that cause climate change, especially from a modeling angle as well?
Yeah, so it's a really important place, right? We've seen so much advancement in Earth observations. We've seen great innovation from the private sector, right? But NASA still really plays this foundational role, not just in the kind of innovation that we've heard about from Miguel, but in terms of that sort of system approach, right? Really understanding all of the drivers of greenhouse gas, not just emissions, but also sources and sinks, right? So a lot of people don't know, I bet you know, that about half of human emissions of carbon dioxide are absorbed every year by the world's vegetation, by the world's oceans, right? So that's the thing that's saving us from climate change being much farther along, much worse than it is today, right? But one of the challenges we have is we don't know how long that can continue. We don't understand all of the processes that contribute or how to predict them in the future, right? And so NASA's role, the strength that we have of bringing together observations, not just of atmospheric greenhouse gases, but all the surface processes, right? Vegetation greenness, vegetation health, now vegetation structure, ocean productivity, ocean circulation, atmospheric winds, nighttime lights, fires. This is the full court press, and none of those can do it alone. None of those is measuring this exchange of greenhouse gas molecules between the surface and the atmosphere. And it takes that holistic understanding, that suite of satellites and that suite of models to integrate and really understand, that backdrop of how do human emissions interplay with natural sources and sinks that are buffering us from climate change. And I really think that, understanding the big picture, integrating all of that data, and increasingly serving that to the public in this integrated fashion across the federal government. That's what we're trying to do with the greenhouse gas system, right? That's what we're doing with this center, is bringing together the best of the federal government, trying to merge that with industry so that we can provide consistent information. We can increase the access to methods so that people understand and have confidence in why we're giving them these answers. And hopefully others will follow suit, and that you'll have more transparency in the kind of greenhouse gas information that we're able to deliver.
Absolutely. And delivering trusted information and providing these foundational data sets is really a core of what NASA does. So I wanted to touch, John, on your comment about kind of understanding water quality. Goddard really sits, as we talked about, the nexus of satellite development, observations, data analysis to really understand the complex world. Where do you see the progress in accelerating Earth science to action, specifically in the water quality space?
That's a great question. So I love the idea of the blue marble, using this as a way of emphasizing where we've come and where we're going. So a short 78 years ago, we had a grainy black and white photograph of the planet Earth. Folks got lucky. They duct taped the camera onto a Delta II rocket. Yeah. Now we have nearly 20 satellites that are providing routine observations, critical observations, that allow us to make informed decisions of their. So I'll also add, 1946 was also the year of the ENIAC computer. This phone is more than 230 million times faster than that room-sized computer. You talk about innovation, where we're going. So this is NASA's year of open science. Okay, so our jobs are to address and help folks that are then in areas of food security needs and water security needs. These are also the areas of the world that often lack infrastructure and resources for adequate data collection and analysis. This is why it's so important to strategically integrate open science initiatives and cloud-based services so that we can get these data and information to the people that need them. So I see this, as far as having an Earth system science approach, as Leslie mentioned, is key. We can't do this within a bubble. We can't look at this just through one lens. We have to work together. We have to learn from other folks who have done this before us and continue to look for it, because I tell you what, it's, as you've so eloquently highlighted, it's urgent, and we need to approach this from an Earth system science approach.
Thank you.
All right, well, I could continue to ask questions, but I'm guessing that you all have a couple. So for those that are joining us online, please feel free. We're getting them beamed directly to me. But for those that might want to ask a question, please feel free to go to the microphones, and we'd be happy to take them.
What was the name of the good god again?
UKU. UKU is it's a funny folklore because the El Yunque rainforest is one of the most pristine, only tropical forests in the U.S. Forest Service. And El Yunque, they say that UKU protects Puerto Rico, and it's because every time the hurricane comes, UKU scares it off and it goes up north.
It's also called the loop for it.
That as many Americans were killed in Puerto Rico by Hurricane Maria, as were killed on the 9/11 attacks on the World Trade Center. Most people are not aware of that. But and the recent barrel came through the Caribbean earlier this year. Caribou was almost completed. He destroyed.
That's right.
And yeah.
Okay, great. Scientists have been predicting different models for where we would see the carbon dioxide level based on how much action we take. There's the model where we do nothing, then there's a model where we do a lot, and something in the middle. Based on your expertise, where do you see us going? What do you think is a likely projection? What kind of effects do you think could happen based off of the models that you think would likely occur?
Thank you.
Yeah. All right. That's a good question. Look, as you mentioned, there are these scenarios that drive long-term climate projections, and they make certain assumptions about technology and how that's going to evolve, choices that are made within societies all over the world. And they're made to sort of be an envelope of uncertainty of, a very broad range of choices, right? And so rarely are you ever at the lowest scenario of emissions. That's always your best case, or at the worst, So we're somewhere in the middle, right? And I will say, one of the things that is fascinating is that, we see history being written right now, right? This is, we've seen incredible change, incredible action within the U.S. federal government, right? The largest climate change investments from the IRA and the BIL, right? And so those are actively changing the trajectory of the curve. One of the challenges we have, and the things that is exciting about what we do, one of the reasons we're bringing together all of this greenhouse gas data is so that we can watch and track and hopefully show the world that our actions are working and that we're bending the curve, we're reducing emissions, and that these investments have been successful. So I'm saying this not as a way to sort of not give you a specific scenario, but saying, in part, we don't know the answer to that because we're changing the answer right now. And I think that should give us all hope that we are acting in a way that can change these trajectories. And we know that when we do that, the climate can recover and can change in the positive direction. And so I would say, to me, that's the more important takeaway than knowing that we're on the worst case scenario or the best case scenario. We're in the middle, and we're changing that, and we're actively looking at how that's affecting not just greenhouse gas concentrations, but the planet as a whole.
Thank you very much.
Thank you.
Yeah, could I respond to that? I probably shouldn't.
No, go for it.
Your answer was perfect, but of course, it is up to us, and we're changing it right now. We're going to change it again for good or ill 20 days and a few hours from now. It's inappropriate for me to even indirectly say anything about an upcoming political race in a setting like this, to an audience like this. And I get that. But I just want to say, after struggling with this for more than 50 years, climate science is a big part of it. Economics is a part of it. Political economy is a discipline that is not as well known, and even less well known as a discipline invented at the University of Maryland, not far from here, called public choice. A great economist named Mansur Olson began that. What we decide in the political system affects the course of this crisis. We're putting 162 million tons of man-made global warming pollution into the thin blue troposphere every 24 hours. We can stop that. We have everything. We have all the technologies we need according to the International Energy Agency and the IPCC. We have all the technologies we need to cut emissions in half within a decade. And we have a clear line of sight to get to net zero by 2050, by mid-century. If we do, then one of the least understood, I shouldn't be saying this in the presence of people who understand far more than I do, but where the public is concerned, one of the least understood beneficial consequences of shifting over to solar and wind, batteries and circular economies and green hydrogen and regenerative agriculture and forestry. One of the benefits of getting to net zero is, number one, the temperatures on Earth will stop going up immediately. 3 to 5 year lag, according to the IPCC has published this for quite some time. And if we stay at true net zero, then half of the anthropogenic CO2 would fall out of the atmosphere within about 30 years. What goes up must come down.
We actually have observational evidence during COVID from satellites.
Yeah, in repair of COVID, emissions, the concentration dropped 6%. The following year, it went back up 7%. You can go back in time and see the financial crisis of 2007, 2008 as well. But we don't have to link it to the suppressed economic activity the way the pandemic did. We can swap out, and I don't know. I'm sorry. I just wanted to say that when you have a question like that, the answer is, from all of us. I'm going to try to restrain myself.
It's about it. And I'm giving you a new one. Thank you. Thank you for your words. We appreciate it. Absolutely. I think we have time for one or two more questions. So I wanted to make sure that we caught any online. Yeah, okay. So one of these is from Lily, and this is really speaking to what we were talking about, climate change messaging. How can we improve climate change messaging to the public to be more effective and less politically fraught? What are the tools that you all use to connect that you found have really been successful? I don't know, John or Miguel.
I think using examples, the goal here is to go from useful to usable information. And when I talk with my friends, they say, "What do you do?" And I said, "Well, I live in Ellicott City. We've suffered several catastrophic floods, from no water on the ground to water moving SUVs down the water down the main street in 7 minutes." And NASA is contributing to this. Yeah. This is what NASA does. So we have one of the first demonstrations of a machine learning based complementing a stream flow forecasting in Ellicott City. And this is us helping our backyard. That's what we do. That's why we have to do it. I don't have to go around in Ellicott City and remind people of the importance of understanding the impact of a flash flood. And because people understand that. But I think increasing transparency is key, and connecting with people's motivations and needs and what moves them. And what moves the needle for everyone in Ellicott City, Maryland, as being safe, and understanding that we are supporting them and contributing to that.
Absolutely.
John Taken? Yep, we can take a question over there.
Can you hear me? This is a question for all panelists. I would like to ask, what are some of our biggest challenges that we can possibly turn to opportunities for the NASA community here in addressing climate change?
Thank you so much for the question. I might pitch that to Miguel to maybe talk about the opportunities for the atmosphere.
Subseasonal to seasonal prediction is an area that our organization is putting a lot of thrust, strategy, investment, because it tends to be the middle kid between short-term forecasts and ENSO predictions. And we were talking about this over lunch. It's where there are things that you can model if you understand them and you have observed them. But if you haven't observed them, there's basically no way you'll understand them. I hope I'm making sense, right? And for subseasonal to seasonal, we need to understand stratospheric dynamics and the chemistry that's going on in the lower troposphere and the upper stratosphere. What happens every time there's a volcanic eruption or a major fire is it creates massive changes in the atmosphere. And I wish we could see that with our eyes. In the same way we see Landsat images of Las Vegas and we can say, oh, it's growing, definitely something's going on. It's hard to describe and communicate dramatic changes to the atmosphere the way we are measuring them. To solve this problem, a Goddard team is pitching a mission called STRIVE. I forgot the acronym because I'm too new. Stratospheric observations. And the important part of this mission is that it focuses on the limb. Doesn't look at the land. It looks at the entire small piece of the atmosphere where we can get insights into aerosol loading and how that ultimately impacts that 30-day forecast. That right there is the holy grail. If we can get a 30-day forecast in terms of preparedness, in terms of investment in resilience, we wouldn't have to spend $50 billion per hurricane evacuated at $2 million a mile if we had that much time. And that doesn't even talk about the early warning systems that we could offer to our allies who don't have Doppler radars every 2 miles. So we're rich. We have Doppler radars, but what happens if you lose your Doppler radar? You're blind. And so these are the things we are working on, and we're happy to compete with other centers and industry to have a seat and build STRIVE. That's fine. But you need to understand these are critical measurements. And so we're in it.
So, and one of the other missions that Casey Swaled mentioned was the atmosphere observing system.
That's right.
So this is where we're architecting the next generation of observations of precipitation, of aerosols, and how it all interacts to form storms. And we're really looking forward to moving forward with that with Goddard.
Yeah, that is the baseline. STRIVE is sort of the bottom line.
So I think we have time for one very short question. Do you want to take it? Okay.
So first of all, can y'all hear me?
Yes.
Yep.
Fantastic. So I have a question for Leslie. I was wondering, so commercial industry has an increased capacity to measure greenhouse gases like methane. And I was wondering, what does the path forward look like to encourage that development of capacity while still maintaining long-term, high-quality, well-calibrated measurements that the public has access to so that we can measure these changes?
Yeah, this is a really good question. It's one we get a lot, right? Because if you've watched the news, you've seen press releases. Even last week we saw first light images from the Carbon Mapper constellation, which is a public-private philanthropic partnership. So you're seeing all of these technological innovations and innovations in the ways that we work and finance observations, which are incredibly exciting. And one thing that's worth noting is that some of those innovations were enabled by NASA investment, right? Carbon Mapper is a successful transition of years and years of airborne investments by colleagues at JPL demonstrating and refining methods, and then working to deploy those in partnership with a private company like Planet, right? You see lots of other NASA data being used for private companies to develop algorithms and sell data services that might be targeted to certain customer bases, right? So they're going the last mile of data delivery. So there's a lot of enabling that is happened because of NASA's investments in maturing technology. And, now as we see those kinds of observations come in, there's this incredibly important role from the federal government, right, in establishing standards, data integrity, not the things that make the front page of those press releases or those images, but, the ground-based and airborne observations that we have to invest in, the data systems that allow people to test and develop new algorithms, the data services that serve our data and allow others to compare against that so they can demonstrate the fundamental quality of their services so that they can do a better job serving their customers, they can do a better job selling data, and we can enable industry in that way while providing this connectivity between different satellites so that people can understand how to integrate them and also have this long-term record where you may have a dense new observation period that you need to connect against a longer baseline. And so that's why having the continuity of ground-based systems, the continuity of airborne measurements, and those kind of tried and true, global mapper satellites that NASA still strives to deliver with partners like NOAA, that's one of the roles we play in sort of enabling new space, but still providing that foundational capability to tie it all together.
Thank you. Thank you so much.
Could I add a word to that?
Am I going to say no?
And Bud, the same year that that Discover was first imposed, I went to the Los Angeles Museum of Science and proposed the so-called Digital Earth program. And one of the guiding visions was to be able to hover above the Earth at any point in space and drop down through successively denser data sets and to hover just a few meters above any point on the. And NASA hired Keyhole, a private company, and a few years after I left the White House involuntarily, there was Google bought Keyhole, and when you talked about enabling and serving, that was a direct transition from NASA out to what is now known as Google Earth. And the reason why artificial intelligence comes into play now is that you can see methane from space. And again, there are people here who know a million times more than I ever will about this stuff, but forgive me. You can see methane from space, but you have to have a wide area. Having a concentration just on a few big, belches of methane, that's one thing. But to see them all, you need different instruments. And Climate Trace is covering a wide methane measurement. But where CO2 is concerned, the atmosphere is already so enriched with CO2. What is it now? 417 to maybe 422 this month. It's already so enriched with CO2 that you're looking down through a column where the signal to noise ratio is unfavorable. That's where AI becomes crucial by fusing together the infrared images and the visible light images. We can even see the ripples of water in the cooling ponds and the speed of the fan blades that are cooling some of these centers. An approach, by the way, which was derived from NASA's exoplanet research. That's where the measurement of the speed of the fan blades comes from, believe it or not. I mean, of course, it's way above my pay grade. I can't explain it, but it fits in with your. So, thank you for all that you're doing.
Well, and unfortunately we have to close, but I have to give you kudos because I think you're the only vice president that's ever used the term signal-to-noise ratio with a scientist in the right way. Kudos. So thank you, everybody, both in the room and online. I think we had over 800 people watching this online, so thank you so much for your engagement. As we take time to share the insights of the future of Earth observations today, we've only scratched the surface of this multidisciplinary, innovative work being carried out by our dedicated scientists, engineers, and everyone else that contributes to NASA's mission. So I just want to thank everyone on behalf of all of the leadership here for the work you do every day to enable NASA's mission. Thank you.